Welcome to Study Loop.
So let's say the two solenoids here are solenoid 1 and solenoid 2, such that the diameter of solenoid 2, that is the second solenoid, is equal to twice of the diameter of solenoid 1. Now the inductance of the solenoid is given by mu naught n square A over L, and area of a solenoid is area of the cross section of the solenoid, so that will be equal to pi r square. And since r is half of d, that is radius is half of the diameter, so we have d over 2 whole square in place of r square, and then L in the denominator. So this will be equal to mu naught n square pi d square over 4L. Now the length of the wire is a constant and is equal to n times pi times the diameter of the solenoid. And since for both the solenoids we have this relation, let's call this equation 1, and length of the wire is a constant, therefore we can say that n is inversely proportional to the diameter of the solenoid. And then from this relation, equation 1, we can say that n of solenoid 1 will be equal to twice of n of solenoid 2. Basically, since they're inversely proportional, so if one solenoid increases by some factor, then n for the same solenoid will decrease by the same factor. So that's there. And the fact that the wire is tightly wound gives L of the solenoid to be n times d of the wire. And now we can find the ratio of the two inductances. So L2 over L1, so I'm starting with equation 2. So this will be equal to mu naught pi over 4 n2 square. So 2 stands for the second solenoid and 1 stands for the first solenoid. So n2 square times d square solenoid 2 over length of solenoid 2 over mu naught pi over 4 and 1 square d square solenoid 1 over L of solenoid 1. And then, so this whole expression cancel out because it's common in both. Now we will use the relations that we have. So n1 is equal to twice of n2. That's one relation. Then we have d of solenoid 1 to be equal to twice of d of solenoid 2. That relation. And then we have another relation, that is n is equal to, so let me just express this in terms of n. So n is equal to L of solenoid over d of wire. Or we can also write this to be equal to L of wire over pi d of solenoid. So this comes from the third relation, equation 3. So here we are going to use this relation for n1 and n2 and substitute that over here. So that will give us L square over pi. So let me just write n2 and n1 first, and then we can take the square of that. So from here we say that this is L wire over pi d of solenoid 2, and length of the wire is a constant, so doesn't matter which solenoid we are using, length of the wire is a constant, so we will be using the same notation. And then square, then the rest of the term over, again length of the wire over pi d solenoid 1 whole square times d square solenoid 1 over L of solenoid 1. Let's move on to the next page. So we do a little bit of simplification, and that results in cancelling out the d square for both the solenoids. So we have d square over here, then over here as well. So these two cancel out, and again these two cancel out. So we are left with L wire square over L of solenoid 2 over L wire square over L of solenoid 1. Also the pi terms cancel out because they are common in both numerator and denominator. And this again we can cancel the length of the wire. So L2 over L1 becomes length of solenoid 1 over length of solenoid 2. And this we can write from equation 4, this one, to be equal to, okay, I didn't box it properly, so not that one. So basically this is the one. Let's call this equation 4. So we will use this over here. So this will be equal to n1 d of wire. So diameter of the wire is also a constant, so we are using the same notation. So we get L2 over L1 to be equal to N1 over N2, and now we can use equation 3 and see that L2 over L1 will be equal to 2. So inductance of the second solenoid is twice of the inductance of the first solenoid. Thank you.